Picture a single production facility growing more than 100 million algae cells in every milliliter of water. That is 100 billion cells in just 1 liter. Now imagine photobioreactors and open pond systems stretching across hundreds of acres, producing thousands of tons of living microorganisms every single year. This is not a vision of the distant future. This is algae farming happening right now across the United States and around the world. How do farms cultivate these microscopic organisms at industrial scale? What keeps billions of tiny cells alive and multiplying in massive cultivation systems? And why are major energy companies and nutrition corporations investing hundreds of millions of dollars into this revolutionary form of agriculture? Welcome to AgriCraft, where we explore the cutting-edge technologies and innovative practices transforming American agriculture and global food systems. Today we dive deep into the fascinating world of algae cultivation, from selecting the perfect strain to processing plant operations, revealing every step of how these ancient organisms are becoming the superfood and biofuel of tomorrow. All will be revealed in this video. Algae are among the oldest living organisms on Earth, having existed for more than 3 billion years. These simple photosynthetic organisms range from single-celled microalgae invisible to the naked eye, to massive seaweeds stretching dozens of meters long. For our purposes today, we focus on microalgae, the microscopic species that hold the greatest promise for industrial cultivation. Long before humans walked the Earth, algae were quietly performing one of the most important jobs in planetary history. Through photosynthesis, these tiny cells converted carbon dioxide into oxygen, gradually transforming our atmosphere and making life as we know it possible. Today, that same process makes algae incredibly valuable for both environmental and commercial applications. Indigenous peoples in Africa, Asia, and the Americas have harvested wild algae for food for thousands of years. The Aztecs collected spirulina from Lake Texcoco in Mexico, drying it into cakes for nutrition. Communities around Lake Chad in Africa still harvest spirulina using traditional methods, scooping the naturally occurring algae from the water and spreading it to dry in the sun. Modern commercial algae farming began in the 1950s and 60s when researchers in Japan, the United States, and Europe started experimenting with controlled cultivation. The initial focus was on spirulina and chlorella, 2 species with high protein content and relatively simple growing requirements. The global algae products market was valued at approximately $1.5 billion in 2023. Projections suggest this could reach over $8 billion by 2035, as applications expand in nutrition, biofuels, animal feed, cosmetics, and pharmaceuticals. Here is something that surprises most people. Algae can produce up to 50 times more oil per acre than the best oil-producing crops like soybeans or palm. Some species of microalgae contain over 50% oil by dry weight, making them extraordinary candidates for biodiesel and renewable jet fuel production. The United States military has successfully tested jet fuel derived from algae, and several commercial airlines have completed flights using algae-based aviation fuel. The nutritional profile of many algae species rivals or exceeds traditional superfoods. Spirulina contains approximately 60 to 70% protein by dry weight, higher than beef, chicken, or soybeans. It also provides vitamins, minerals, and antioxidants. Chlorella offers similar nutritional benefits and is particularly rich in chlorophyll, the green pigment that gives plants their color. Beyond nutrition and fuel, algae farming offers environmental benefits. During growth, algae consume carbon dioxide at rates far exceeding land-based plants. 1 kilogram of algae biomass requires approximately 1.8 kilograms of carbon dioxide, effectively removing greenhouse gases from the atmosphere. Some facilities position their algae farms next to power plants or industrial facilities, capturing waste carbon dioxide emissions and converting them into valuable biomass. Now let us explore exactly how modern farms grow these microscopic organisms at massive scale using sophisticated cultivation systems and precise environmental controls. Every algae farming operation begins with selecting the right strain for the intended purpose. Scientists have identified tens of thousands of algae species, but only a few dozen are commercially cultivated. Each strain has unique characteristics regarding growth rate, oil content, protein levels, and environmental requirements. For biofuel production, farms typically choose species like Nannochloropsis or Scenedesmus, which accumulate high levels of lipids or oils in their cells. For food and nutrition applications, spirulina and chlorella dominate the market due to their nutritional profiles and established safety records. Other specialty strains produce valuable compounds like astaxanthin, a red pigment used in aquaculture feed and nutritional supplements, or beta-carotene, the orange compound found in carrots that our bodies convert to vitamin A. Strain selection involves extensive laboratory testing. Researchers grow candidate strains under various conditions, measuring growth rates, oil or protein production, and resilience to temperature fluctuations or contamination. The best performing strains move forward to pilot-scale testing before deployment in full commercial production. Once a strain is selected, cultivation begins in laboratory conditions. Technicians maintain master cultures in small flasks containing sterile growth medium. This medium is essentially water-enriched, with nutrients that algae need, including nitrogen, phosphorus, potassium, and trace minerals like iron, magnesium, and zinc. The laboratory cultures live in climate-controlled rooms with precise light cycles. Most photosynthetic algae require light for growth, converting light energy into chemical energy through photosynthesis just like plants. However, unlike field crops that rely on sunlight, laboratory cultures often use LED lights programmed to provide optimal wavelengths and intensities for maximum growth. Temperature control is critical. Most commercially cultivated algae species thrive between 20 and 30 degrees Celsius, roughly 68 to 86 degrees Fahrenheit. Temperatures outside this range slow growth or kill the cells entirely. Laboratory incubators maintain exact temperatures 24 hours a day. From the laboratory flasks, successful cultures move to progressively larger containers in a scaling-up process. Cells from a 1-liter flask might transfer to a 20-liter carboy, then to a 200-liter tank, and eventually to outdoor cultivation systems holding thousands or millions of liters. This scaling process requires careful attention to contamination prevention. Unwanted bacteria, fungi, or competing algae species can invade cultures and outcompete or kill the desired strain. Sterilization of all equipment, filtration of water and air, and strict hygiene standards protect the cultures during these vulnerable early stages. The outdoor cultivation systems fall into two main categories: open ponds and closed photobioreactors. Open pond systems are the most economical approach for large-scale algae farming. These are shallow ponds, typically 20 to 30 centimeters deep, arranged in raceway configurations that look like winding tracks. Paddle wheels continuously circulate the water, keeping algae cells suspended in the liquid and exposing them to sunlight and carbon dioxide from the air. Open ponds can cover enormous areas. Some facilities in the southwestern United States operate pond systems spanning over 100 acres. The ponds are usually constructed by excavating shallow depressions and lining them with plastic or clay to prevent water from seeping into the ground. The major advantages of open ponds include low construction costs compared to closed systems, and the ability to scale up to very large production volumes. However, they face significant challenges. Weather conditions directly affect algae growth. Cloudy days reduce photosynthesis. Rain dilutes the culture. Temperature extremes stress or kill the cells. Contamination is another persistent issue with open ponds. Wild algae species, bacteria, and predatory organisms like rotifers or amoebas can enter the ponds from the air or local environment. Once established, these contaminants can devastate the desired algae culture. Farm managers combat this through strain selection, choosing robust algae species that can outgrow most competitors, and through careful monitoring and rapid response when problems appear. Closed photobioreactors offer greater control but at higher cost. These systems consist of transparent tubes or flat panels made from glass or plastic, filled with algae culture and sealed from the external environment. The tubes might be arranged in long parallel rows, serpentine configurations, or vertical towers depending on the facility design and available space. Photobioreactors allow precise control over every aspect of the growing environment. Carbon dioxide is injected directly into the culture at optimal concentrations. Temperature is regulated through cooling or heating systems. Light exposure can be supplemented with artificial lighting when sunlight is insufficient. The closed design prevents contamination from outside sources. Some of the most advanced photobioreactors use automated systems to monitor and adjust conditions in real time. Sensors measure cell density, pH levels, dissolved oxygen, temperature, and light intensity. Computer systems analyze this data and automatically adjust pumps, valves, and lights to maintain optimal growing conditions. The cultivation medium in both open and closed systems requires careful nutrient management. As algae cells multiply, they consume nitrogen, phosphorus, and other nutrients from the water. Farmers must regularly add fresh nutrients to maintain growth rates. Too little nutrition and growth slows. Too much and excess nutrients are wasted, increasing costs and potentially causing environmental problems if wastewater is not properly treated. Many facilities use agricultural or industrial waste streams as nutrient sources. Wastewater from food processing plants, dairy operations, or municipal sewage treatment contains nitrogen and phosphorus that algae can utilize. This creates a beneficial relationship where the algae farm cleans the wastewater while obtaining free nutrients, reducing costs and environmental impact simultaneously. Carbon dioxide supplementation significantly boosts algae growth. While open ponds rely primarily on atmospheric carbon dioxide, closed photobioreactors inject concentrated carbon dioxide gas. Some facilities pipe an exhaust from nearby power plants, ethanol distilleries, or other industrial sources. The algae consume the carbon dioxide during photosynthesis, reducing greenhouse gas emissions while accelerating their own growth. Growth rates in optimized systems can be remarkable. Under ideal conditions, algae biomass can double every 24 hours or even faster. This exponential growth is what makes algae so attractive for industrial production. Imagine planting a field of wheat and watching it double in size every single day. That is essentially what happens in an algae cultivation system. Harvesting algae presents unique challenges because the cells are microscopic and suspended in large volumes of water. A typical algae culture might contain only 1 to 5 grams of dry algae per liter of water, meaning the harvest process must separate tiny cells from approximately 99% water. The timing of harvest depends on cell density and the specific production goals. For continuous production systems, farmers harvest a portion of the culture daily or every few days, while leaving enough cells behind to keep the culture growing. This maintains steady production rather than boom and bust cycles. For batch production systems, the entire culture grows until reaching maximum density. Then the whole batch is harvested, and the system cleaned and restarted with fresh culture. Batch systems allow more thorough cleaning between crops, reducing contamination risks but requiring more labor and downtime. The first stage of harvesting typically involves concentration. Several methods exist for this crucial step. Flocculation is widely used in large-scale operations. Chemical flocculants are added to the culture, causing the individual algae cells to clump together into larger particles called flocks. These flocks are heavy enough to settle to the bottom of settling tanks, or can be more easily removed by subsequent filtration steps. Common flocculants include aluminum sulfate, ferric chloride, or organic polymers. The choice depends on the algae species, the intended use of the final product, and regulatory considerations. Centrifugation uses spinning force to separate algae cells from water. Industrial centrifuges spin the culture at high speeds, thousands of revolutions per minute, creating forces that push the denser algae cells to the outside, while less dense water remains toward the center. The separated algae paste is collected while the water is recycled back to the cultivation system. Centrifugation is highly effective and produces very concentrated algae paste. But the equipment is expensive and requires significant energy to operate. Filtration systems use membranes or screens with pore sizes small enough to trap algae cells while allowing water to pass through. Different types of filtration include microfiltration, ultrafiltration, and tangential flow filtration. These systems can process large volumes of culture quickly and work well for many algae species. However, membranes can clog and require regular cleaning and replacement. Some facilities use dissolved air flotation, where tiny air bubbles are mixed with the culture. The bubbles attach to algae cells and carry them to the surface, where they form a concentrated layer of foam that can be skimmed off. This method works well for species with appropriate surface characteristics. After initial concentration, the algae slurry still contains substantial water, perhaps 80 to 90%. Additional dewatering steps are usually necessary. This might involve pressing the slurry through filter presses that squeeze out more water, additional centrifugation, or moving directly to drying processes. The concentrated algae paste moves from the harvesting area to the processing plant, usually within hours of collection. Time is critical because once separated from their growth medium, algae cells begin to deteriorate. Cellular enzymes start breaking down proteins and lipids, and bacteria can multiply in the moist, nutrient-rich paste. Rapid processing preserves quality and nutritional value. In facilities producing living algae cultures for aquaculture feed or research purposes, the harvest process is gentler. These operations might use gravity settling or gentle filtration to concentrate the cells while keeping them alive and healthy for transport to customers. The processing plant transforms wet algae paste into stable, marketable products. The specific processing steps depend entirely on the intended end use, but several common procedures appear across most facilities. Drying is almost always necessary to create shelf-stable products. Wet algae paste will spoil rapidly at room temperature, so removing water is essential for preservation. Several drying methods are employed in industrial operations. Spray drying is perhaps the most common method for producing algae powder for food and nutrition markets. The algae paste is atomized into tiny droplets and sprayed into a chamber with hot air flowing at temperatures between 150 and 200 degrees Celsius. The droplets dry almost instantly, falling to the bottom of the chamber as fine powder. Spray drying is fast and produces powder with good nutritional retention, though the high temperatures can damage some heat-sensitive compounds like certain vitamins or pigments. Drum drying involves spreading algae paste in a thin layer on the surface of heated rotating drums. The paste dries as the drum rotates, and scrapers remove the dried material as thin flakes. This method uses lower temperatures than spray drying and can be gentler on the product, but processing capacity is lower. Freeze drying produces the highest quality dried algae by freezing the paste and then removing the water through sublimation in a vacuum chamber. This preserves more nutrients and active compounds than heat drying, but the equipment is expensive and the process is slow, making freeze-dried algae a premium product sold at higher prices. For biofuel applications, the processing pathway is completely different. The goal is to extract oils or lipids from the algae cells. This typically starts with cell disruption to break open the cell walls and release the internal contents. Several disruption methods exist. Mechanical disruption uses high-pressure homogenizers or bead mills that physically break the cells apart through shear forces or grinding. Chemical disruption uses solvents or enzymes to dissolve cell walls. Some facilities use sonication, employing high-frequency sound waves to rupture cells. Once cells are disrupted, oil extraction begins. Solvent extraction is widely used, where organic solvents like hexane dissolve the lipids, separating them from proteins, carbohydrates, and cellular debris. The solvent and oil mixture is then separated from the solid material, and the solvent is evaporated and recycled, leaving pure algae oil. Supercritical carbon dioxide extraction is a more advanced method that uses carbon dioxide under high pressure and temperature conditions, where it behaves as both a gas and liquid. This supercritical carbon dioxide dissolves lipids efficiently and leaves no toxic residues, making it attractive for food-grade oils or high-value applications. However, The equipment is expensive and complex. The extracted algae oil can be used directly in cosmetics or nutritional supplements, or it can be converted into biodiesel through a process called transesterification. This chemical reaction converts the triglycerides in algae oil into fatty acid methyl esters, the technical name for biodiesel, and glycerin as a byproduct. Quality control and quality inspection happen throughout processing. Laboratories test samples for moisture content, protein levels, lipid composition, and contamination. For food products, testing includes microbial analysis to ensure the product is safe. Standards vary by country and intended use, but facilities producing algae for human consumption follow strict food safety protocols similar to other food processing operations. Temperature control during processing is crucial. Excessive heat damages proteins and vitamins. Inadequate heat treatment may allow bacterial survival. Industrial machines monitor temperatures continuously, and automated systems adjust heating or cooling to maintain optimal conditions. Cleaning and hygiene standards in processing plants must be rigorous. Equipment that contacts algae products is typically made from stainless steel or food-grade plastics. Regular cleaning with approved sanitizers prevents cross-contamination and bacterial growth. Workers follow good manufacturing practices, wearing protective clothing and following strict protocols for hand washing and equipment sanitization. Some processing plants fractionate the algae into multiple products. For example, after extracting oil for biodiesel, the remaining meal is rich in protein and can be sold as animal feed or further processed into protein isolates for human nutrition. Pigments like astaxanthin or phycocyanin can be extracted separately and sold to aquaculture or supplement companies. This fractionation maximizes revenue by creating multiple value streams from a single harvest. After processing, finished algae products move to packaging areas where automated systems prepare them for storage, shipping, and sale. For powdered algae products like spirulina or chlorella tablets and powders, packaging typically involves automated filling machines that dispense precise amounts into containers. Retail products might be packaged in plastic bottles, jars, or resealable pouches. Commercial quantities for ingredient customers are often packaged in large bags or drums holding several kilograms. Labeling requirements for food products are strict. In the United States, the Food and Drug Administration requires nutrition facts, panels, ingredient lists, allergen statements, and contact information. Labels must accurately represent the contents and cannot make unsubstantiated health claims. For liquid products like algae oil or concentrated extracts, filling equipment dispenses material into bottles or containers, followed by capping and labeling machines that apply labels and safety seals. These operations often run on automated conveyor belts with minimal human intervention, ensuring consistency and efficiency. Modified atmosphere packaging is sometimes used for premium algae products. This involves replacing the air inside the package with nitrogen or other inert gases before sealing. This prevents oxidation, extending shelf life, and preserving color, flavor, and nutritional quality. Temperature-controlled storage is important even for dried algae products. While stable at room temperature, storage in cool, dry conditions further extends shelf life and prevents degradation of sensitive compounds like omega fatty acids or vitamins. Some facilities maintain dedicated cold storage areas with temperatures between 10 and 15 degrees Celsius. Distribution channels for algae products are diverse and expanding. The nutritional supplement industry is a major market, with spirulina and chlorella appearing in health food stores, pharmacies, and online retailers across the United States and worldwide. These products market themselves as superfoods, protein supplements, or detoxification aids. The animal feed industry increasingly incorporates algae into formulations for aquaculture, poultry, and livestock. Fish farmers particularly value algae, rich in omega fatty acids and pigments that enhance the color of salmon and other fish. Poultry producers add algae to layer feed, claiming it improves egg yolk color and nutritional content. Cosmetics companies purchase algae extracts and oils for use in skincare products, shampoos, and other personal care items. Marketing emphasizes natural origin, antioxidant properties, and moisturizing benefits. The biofuel sector remains a developing market for algae products. While several pilot projects have successfully produced algae biodiesel and jet fuel, economic viability at commercial scale remains challenging. Current biofuel markets rely heavily on government incentives and mandates for renewable fuels. As technology improves and production costs decline, the biofuel applications of algae may expand significantly. Pharmaceutical and biotechnology companies source specialty algae compounds for research and drug development. Certain algae produce unique molecules with potential applications in medicine, including anti-inflammatory compounds, immune system modulators, and antimicrobial substances. International shipping of algae products happens through standard freight networks. Dried powders and tablets are stable and easy to transport, requiring no special handling beyond protection from moisture and extreme temperatures. Liquid products may require temperature control during transport. Regulatory compliance is essential, with documentation proving product safety, origin, and compliance with import regulations in destination countries. Algae cultivation generates several valuable byproducts and offers unique benefits beyond the primary products. The water used in algae cultivation is typically recycled multiple times. After harvesting, the water still contains nutrients and can return to the cultivation system. This closed-loop approach minimizes water consumption, an important consideration particularly in arid regions where many algae farms operate. The oxygen produced during algae photosynthesis is released into the atmosphere in open ponds or can be captured and sold from closed photobioreactors. Some facilities supply oxygen to aquaculture operations or wastewater treatment plants that use aeration systems. Residual biomass after oil extraction is valuable as high-protein animal feed. This algae meal contains 40 to 50% protein and provides amino acids, minerals, and vitamins. Research shows that incorporating algae meal into animal diets can improve growth rates, immune function, and product quality. Nutritionally, algae offer impressive benefits. Spirulina provides all essential amino acids, making it a complete protein source. It contains iron, calcium, magnesium, and potassium. Vitamin content includes B vitamins, particularly B12, which is rarely found in plant sources. This makes spirulina especially interesting for vegetarian and vegan diets. Chlorella offers similar nutritional benefits with particularly high concentrations of chlorophyll and a unique growth factor that some researchers believe supports cellular health. It also provides nucleic acids, RNA and DNA, which some advocates claim support cellular repair. Both spirulina and chlorella contain antioxidants that protect cells from oxidative damage. These include carotenoids, phycocyanin, and various polyphenols. Research continues into potential health benefits, though consumers should approach marketing claims cautiously and consult healthcare providers. Environmental benefits of algae farming extend beyond carbon dioxide capture. Algae systems can treat agricultural runoff, municipal wastewater, and industrial effluent, removing excess nitrogen and phosphorus that otherwise cause harmful algal blooms and dead zones in rivers and coastal waters. This nutrient recovery creates value from waste while protecting water quality. Land use efficiency is extraordinary compared to traditional crops. Algae can produce 10 to 50 times more biomass per acre than soybeans, corn, or other oil crops. This productivity means biofuel from algae could theoretically replace significant petroleum consumption without competing for agricultural land needed for food production. However, challenges remain. Production costs for algae products are still higher than many competing alternatives. Growing algae for biofuel must compete economically with petroleum, which benefits from established infrastructure and economies of scale. Growing algae for food and feed must compete with soybeans, fish meal, and other conventional protein sources. Energy inputs for cultivation, harvesting, and processing can be substantial. Pumping water, operating centrifuges, and drying biomass all require energy. For biofuel applications to be truly sustainable, the energy output from algae fuel must significantly exceed the energy input for production. Current systems are improving, but many still show marginal energy returns. Research continues to address these challenges through genetic improvement of algae strains, optimization of cultivation systems, and development of more efficient harvesting and processing technologies. Some scientists use genetic engineering to create algae strains that produce more oil, grow faster, or tolerate harsh conditions better than wild strains. From selecting the perfect microscopic strain to packaging finished products for global distribution, the journey of algae through modern industrial farming reveals how ancient organisms are being harnessed for 21st century challenges. What began billions of years ago as simple cells floating in prehistoric oceans has evolved into a sophisticated agricultural industry, combining biology, engineering, and data science. Today, facilities across the United States and around the world cultivate millions of liters of algae culture daily, producing thousands of tons of biomass for applications ranging from nutritional supplements to renewable fuels. The cultivation process, whether in open ponds stretching across desert landscapes or in precisely controlled photobioreactors, demonstrates remarkable efficiency. These microscopic organisms double their biomass daily under optimal conditions, converting sunlight, carbon dioxide, and basic nutrients into valuable proteins, oils, and compounds that benefit human health and environmental sustainability. Processing plants equipped with industrial machines transform the harvested cells into diverse products through automated systems that maintain rigorous quality standards. From spray drying towers producing superfood powders to extraction equipment isolating valuable oils, these facilities represent the convergence of agriculture, technology, and food processing innovation. The distribution networks carrying algae products to consumers span the globe, supplying health food stores, supplement manufacturers, cosmetics companies, aquaculture operations, and research laboratories. As production techniques improve and costs decline, applications will expand further into biofuels, pharmaceuticals, and emerging markets yet to be fully developed. Algae farming addresses critical challenges facing modern agriculture and society. The ability to produce protein using minimal land and water, to capture carbon dioxide from industrial emissions, and to create renewable fuels without competing for food, cropland makes this form of cultivation increasingly relevant. While challenges remain around economic viability and scaling production, the trajectory is clear. Investment continues to flow into the sector, technology advances rapidly, and consumer acceptance grows as people learn about the nutritional and environmental benefits these microscopic organisms offer. Thank you for watching AgriCraft. If you found this deep dive into algae cultivation fascinating, please give this video a like. Subscribe to our channel for more content, exploring cutting-edge farming documentary topics and American agriculture innovation, and leave a comment below sharing your thoughts on algae as food or fuel. Until next time, keep exploring the remarkable frontiers of modern farming and agriculture technology.